Okay guys, Math 6610, this is the second video I think of week 3. What I'm going to do in this video is give you a complete example of carrying out an Anova. Everything from cleansing our data, importing it into R, running the analysis, looking at descriptives, checking assumptions, running effect sizes. We may even look at some power. What do we do when things go wrong will be the final thing that I'll take a look at. So let's get going. I chose really a non-interesting data set, which could come under a lot of fire, really. And what I've got here is I've got some quiz scores for an experimental design where the researcher looked at the sleep and the quiz scores. So what happened? We have 5 participants that were only allowed to get 4 hours sleep, and this exam was actually I think given at 8 a.m. in the morning. So these people went to bed pretty late. These people got 6 hours, and these people got 8 hours, and these are the scores on what I think was a 10-point quiz. So it must have been a pretty tough quiz because the scores are kind of low. Now, I'm not really that. To me, this study just within itself could come under a lot of fire for various reasons, and I'm not really worried about that right now. You'll get into those things when you take the 6996 class, if you take that, when you get into the research sequence. But for right now, what I want to do is just run the analysis and show you the complete illustration. All right, gang, first thing we need to do is we need to cleanse the data and get it into a format that is workable in R. So what we need here, instead of having our measurements given across the 3 levels separately, what we need to do is we need all of our measurements in one column. And this is the way I typically do this. Okay, and for lack of a better title, I'm going to call this quiz, and then I'm going to call this sleep. Now you got to think, in this study there are 2 variables, quiz and sleep, and the way I always want you to set up your data sets in Excel, well, eventually it's going to be in CSV format, but is the variables vertically, and then the participants or the subjects horizontally. So what we need here is we need these folks to have 4 hours. So I'm going to enjoy a nice cool feature in Excel which allows me to drag that down. The next is going to be 6 hours. So drag down 5 of those, and the next is going to be 8 hours, and drag that down. Now guys, we could, in this format right here, we could import this into R and we could carry out the analysis this way. The reason I want you to go ahead and get accustomed to entering the data this way is that's the correct way to do it, and that's the way that some of our more complicated designs are going to be carried out. So guys, once I get that, I'm going to delete this part. I don't need that, and I'm going to come up here and do a save as. And what I want now is I want something simple. I don't want a lot of words. I just want one word, either all uppercase or all lowercase, and I'm going to save it to my desktop, and I need to come to .csv. Alright gang, let's save it and do continue, and I don't need this anymore, so I'm going to close it down, and I don't need to save it because I've already saved it. Alright gang, what I'm going to do now is I'm going to get into R, and I'm going to open up my data. So the first thing I have to do is set my working directory. Now, let me back up. If you're starting new on a machine, the first thing you probably want to do is get your working directory. And it's going to give you the form that you need to start with. So when I set my working directory, I know I need the form that my current working directory is in, and then just set it appropriately. Guys, next thing I'm going to do is I'm going to import the data in. So I'm going to use read.csv, and I called it quiz because I don't want to fart around and worry about a bunch of words and spaces. And of course, the next thing I've got to do is attach my data. Now, it seems like everybody always wants to look at their data. That's fine. I do when I'm teaching, but if I'm actually performing analysis for something, I typically don't worry about it. Something kind of cool if you want just the names of your data. I'm sorry, the variables of your data set, you can just do names, and you can see that we have 2, quiz and sleep. So those are things that vary from subject to subject. All right, gang. I'm going to jump back over to the blackboard, and then we'll come back and we'll perform some stuff. So let me get this going again. All right, cool. Now, one of the well, I'll tell you what. Let's just let's step back here, and let's go to the next page and talk about the steps for carrying out a complete Anova. Now, guys, this our class has been really I think easy so far. I mean, the only thing we've really looked at are T-Test, independent samples T-Test, a dependent samples T-Test, and I think chi-square. So we've kept it really easy, and in a straightforward Anova like we're running now, it's not much more difficult. But guys, we're going to get pretty crazy, pretty quickly actually. So what I want you to do is go ahead and think about getting organized, because it's going to be easy to watch these videos and say, I understand, I know how to do that. But once we get into more sophisticated designs, it's going to be really nice if you've got some notes and a location where you can go get quick information. So guys, what I would recommend that you do is somewhere in a notebook have R commands. And maybe a 2-column situation where you have the command on the left-hand side and the left column, and the right column you tell what the command does for you. Something else that you need to pay attention to is you need to pay attention to the packages. Some of these commands that we use aren't installed in the package of R that we currently have, so we have to install a package and access the library. So you might want to keep, for example, we're going to run something called a Levine's T-Test. Which we did in a previous video. If you remember, we have to download a car package to be able to do that. So somewhere where you can just thumb over to it quickly, keep that in mind. Well, guys, anyway, the steps, the first step that we'll always want to do is cleanse our data. And typically what I like to do is have my data in Excel and cleanse it, get it ready to import into R, and save as a .csv, and then go for it. The next thing that we'll do in this case, and actually in all cases, we'll check assumptions. Now for Anova, we have 3 assumptions. One, as I discussed in the previous video, is we assume that we have equal variances across our K groups. Another assumption is that we have normality. And what I really mean by normality is we have group normality. We can look at our quiz scores, for example, across all four groups, but in this situation I would be more concerned, do I have normality for the measurements in each group? So I'm going to show you using what's called a Shapiro test. I'm going to show you how to test that. And guys, by far the most important is the assumption of independence. We don't want any relationship between our measurements. Now, just well, I'll tell you what. I'll get to that. A little bit later. The third thing that I want you to become accustomed to doing is don't forget your descriptives. Well, guys, for some reason, that part of my iPad doesn't like to write. And the third part is explore your data. And all I mean by this is don't forget to compute your descriptive statistics. Look at histograms, look at box plots, calculate means, calculate standard deviations. The fourth thing you do is run your basic analysis. That's the easy part, usually. The fifth thing I want you to do in this case is run your post-hoc. And there's many post-hocs that we can look at, Tukey, Bonferroni. For the Anova situation, I'm going to teach you the Bonferroni. And guys, the sixth thing that I want you to get accustomed to doing is reporting your effect size. And then, of course, the final thing, report your results. Put these things in writing. So, guys, that's what we're going to do here. We're going to take this very, very simple, small data set, and we're going to run through these things. All right. You know what? I say let's just go ahead and do it. So let's get back into R, and the very first thing I'd want to do is check assumptions. And for me to be able to check I'm not smart enough to type and talk at the same time. So guys, remember this hashtag out here lets me communicate with you without actually doing an R command. So the first thing I'll do is check homogeneity of variance assumptions. And what I'm going to use, I'll use Levine's test of homogeneity of variances. Now guys, the null hypothesis is the variances are all equal, while the alternative is at least one pair of variances are different. Now, to be able to carry out the Levine's test of homogeneity of variances, we have to download, or I should say install, the CAR package. So I've got to go install packages. Remember, when we do this, we have to put the name of the package in quotations. Now, it's going to allow us to choose a CRAN, and I just like these folks at UCLA. They have an amazing statistics department. So they're located at USA California 2, so I'm going to choose that. Now, depending on the speed of your computer, it's going to go through some stuff. So I've got a lot going on my computer running, and so it's going to take a little while. And the next thing I have to do here is I have to bring up the library for CAR. Now notice that when we install the packages for CAR, CAR has to be in quotations. When we access the library, it does not. Well, guys, we're ready now. So Levine test, and we want first of all quiz over the factor, which is sleep. And guys, I want the center to be equal to the mean. Now, when we carry this out, remember the null hypothesis is the variances are all equal. And you can see that our p-value is way higher than 0.05. So therefore, well, we'll assume equal variances. All right, second, we'll check for normality using the Shapiro test. Now, Shapiro test, as far as I know, I don't think it's included in the CAR. I think it's just included in the initial download of R. But we'll want to do a couple of things here. The first thing I'd want to do is I'd want to carry out the Shapiro test just for quiz. Now this is going to look at the quiz scores irrelevant of whether they came from the 4, 6, or 8 hour. And well, I should have told you this. The null hypothesis, the Shapiro test, is the distribution is normally distributed. The alternative hypothesis is the distribution is not normally distributed. So you can see here that we do not have statistical significance. So there's not enough evidence to conclude that we have that we can reject the claim that the distribution is normal. You know, it appears that the second assumption is also satisfied. Now, I think what's probably better here, it's best to test for normality for quiz across sleep hours. So what I would do here is I would use the by function, and I would first have my quantitative, which is quiz, across my factor, which is sleep, and then I would bring in the Shapiro test. I didn't spell that correctly, did I? Now what this is going to do is it's going to give us the test for normality across the levels of our categorical variable. And you can see for 4 hours, 6 hours, and 8 hours that in all cases we don't have statistical significance, which is really kind of what you want here. Deviations from normality for the assumption. There's a guy at the University of Cincinnati called, his name's Stevens, who's done a lot of work on this. He's shown that violation of normality isn't that big of a threat to the stability of the p-values for our Anova model. Even violation of the test of the homogeneity of variances isn't a major issue. The violation of independence is critical. So that's something that we test. Really, to me, the test of independence comes in the design of the study. Now, next thing I'd like to do, explore the data. And in other words, calculate the descriptive statistics. So the easiest way to do this is what we call t-apply. And what t-apply allows, well, let me back up. If I wanted to look at the mean of quiz, well, I could certainly do that. If I wanted to look at the standard deviation of quiz, I could certainly do that. If I wanted to look at, if I want to get the 5-number summary, including the quartiles, I could use what's called quantile for quiz. It's going to give me my 5-number summary. The 25% is Q1 and the 75% is Q3. Clearly the median is 3.00. If I didn't trust that, I could do median for quiz and get this. If I wanted to do the variance, I could do it correctly and get a variance of 3.12. Alright gang, but in this situation what I'd like to be able to do is I'd like to be able, more so than looking at the mean standard deviation for the quiz of all the measurements for all sleep, I'd like to be able to calculate the mean standard deviation, descriptive statistics in general for quiz across the levels of sleep. And to do that, what I would do is I would do t-apply, and what goes first for t-apply is my quantitative. Secondly, I put in my categorical, and then I just put in the descriptive statistic measure that I want to take a look at. So you can see now the quiz has been, that the mean has been presented over the 3 levels of sleep. Okay, same thing if I wanted to. I could clearly look at the standard deviation. Guys, this applies for all descriptive statistic measures. The next thing I want to do is I would probably want to look at a box plot. And it's not going to be really exciting here because we've only got 5 measurements, but if I wanted to look at a box plot, I could use this notation. And what this is going to give me, it's going to give me a side-by-side box plot, and gives me the potential to compare the 5-number summary and also to see if there are outliers across the groups. Well, you can see we have no outliers, and you can see that the IQRs, which is the width of the box, are pretty similar across 4 hours, 6 hours, and 8 hours. And again, we have no outliers, so that's something that we would want to report in our descriptive statistics stuff. Alright gang, what I would do now is I would want to run the Anova. I'm going to need the Anova results later on, so I'm going to call it something. And you can call it whatever turns you on. I call it model because I just do. And our Anova model, we just use AOV, and we use kind of the same notation we did for the box plots. So we put our quantitative variable in, tilde the categorical variable. Now we're not going to get anything, but I can type model and I can see I get the sum of squares and degrees of freedom for the Anova. What I really am most interested in is the full effect, the full presentation of the Anova output, and I get that by summary model. And the guys, remember, this is presented in terms of sleep, but this is our degrees of freedom, sum of squares, mean square for our between, and this is our degrees of freedom, sum of squares, and mean square for our within terms. Now what's most important here, well, not most important, but what's important is we have an F value of 5.12 and we have a P value of 0.0247, so we have statistical significance at the 0.05 level. We do not have statistical significance at the 0.01 level, because if we did, we'd have 2 asterisks there. So guys, recall the null for an Anova is the means are equal, while the alternative is at least one pair of means is, let's see, at least one pair of means is different. So guys, what we can say here, we have statistical significance, so we have one pair of means that appears to be statistically significant. Now, if I go back to my descriptives, right back here on my means, and we don't want to get caught up in this trap, but it looks like to me that between the 4-hour and 6-hour, notice that the mean difference is only 1 hour, or I'm sorry, one difference in the quiz score. That probably isn't going to give me statistical significance. Between 6 and 8 hours, I have 1.8 difference. Don't know. between 4 hours and 8 hours, I have 2.8. So I'm probably now thinking that the difference is probably between the 4 hours and the 8 hours, but there's a possibility that there's a difference between the 6 hours and the 8 hours. In fact, there's a possibility that there's even a difference here. But with this small sample size, I don't think the standard error would be sufficient to make that happen. Okay? So guys, we now know we've got something going on, so what we want to do now is we want to run a post-hoc analysis. Now we can't be reminded, we can't run straightforward t-tests because this would inflate the type 1 error rate, and we're not willing to do that. So what we have to do is we have to run post-hoc analysis that have been created to control for, it kind of adjusts the calculations of the p-value where the type 1 error rate is not inflated. Now there are different ones. There's Bonferroni, there's Tukey HSD, there's a Chaffee, there's a Benjamini, Hockenberg or something to that effect. I'm going to demonstrate the Bonferroni, and that's the one that I'll want you to use. I mean, it's solid, so I'm not leading you down the wrong road here. So guys, what I would run here is I'd run what's called a Pairwise T-Test. And what I would do here is I would run my quantitative across my categorical. I need to tell R that I didn't do a matched pairs t-test. So I'm not assuming that I have dependence here. And the next thing I do is I'm going to do my p-adjust method to be equal to the Bonferroni. Now, when I do that, it's going to show me that the pairwise comparisons were using individual t-tests with pooled standard deviations. Now, what I'm looking for is I'm looking for statistical significance. And these are the p-values. And again, there's been a p-value adjustment using the Bonferroni method. Well, guys, when I look at the p-value between 4 hours and 6 hours, the p-value is clearly above 0.05. When I look between 6 hours and 8 hours, not statistically significant. But as we kind of predicted, maybe kind of thought, that the statistical significance, the reason way back up here that we found a statistically significant ANOVA result was because of the comparison between the 4-hour and 8-hour. Telling me that the kids, the students, I don't know, I think this was actually in college, so it had been adults. So the students here who got 8 hours sleep, again, the assumption for this, and I'm not sure that they could do this, is all these kids had equal mathematic achievement levels. So it wasn't like smarter kids were 8 hours. So they feel like they could tap into just the difference based on the number of hours of sleep. And I don't know about all that. But they claim that they could do it. But we'll get into it. Pretty soon we're going to get into something called a covariate, which would be much, much, much more appropriate than I think the study they've done here. But I want to keep it kind of simple. All right, gang. Next step is to calculate our effect size. Now, easiest way is to use the summary.lm method. But this method has come under some fire lately. So anyway, let me demonstrate it. So once we've conducted our ANOVA back here, notice I called it model. And I wanted to call it model for a variety of reasons. I wanted to do stuff with it later on for summary and also this step right here. So guys, if I do summary.lm of my model, what it's going to do is going to give me a pretty cool output. And what this does, it puts it back into the more of a general linear model format. Looking at the residuals, it breaks down the coefficients of the general linear model, giving significance levels and test statistics and even standard errors. But what I want you to calculate, or what I want you to focus on in this video for ANOVA is that line right there, the multiple r squared. Now, the multiple r squared value is called Etta Squared. And we're going to run into, unfortunately, because it adds to math confusion, but we're going to run into multiple effect sizes. Well, one effect size that is calculated for ANOVA is called Etta Squared, and it's really easy to get via this operation right here, this command. Now, what we have to do here is we have to take the square root of that. So technically, our Etta square will be the square root of 0.4604. So our Etta square is actually 0.68. Now, the threshold, or the benchmark, for Etta square is 0.1, 0.3, and 0.5. Now, what I mean by that is 0.1 is gives or represents a low effect, 0.3 represents a moderate effect, and 0.5 represents a large effect. Now, guys, this is going to get crazy after a while because we're going to have different effect sizes. So here's what I've done. I have gone into Blackboard, and let me just bring that up here. I've gone into Blackboard, and right above week 1, week 2, week 3, I've given you a link which says effect size magnitudes. Now guys, if you click that, you're going to be directed to this site right here. This site right here gives you all of the effect sizes, the different effect sizes. We've already looked at Cohen's D, we've looked at Cohen's F, we're looking at Etta squared, we're getting ready to look at omega squared, and it gives you over here the small, medium, and large. It gives you the benchmarks for what we associate with a small effect, medium effect, and a large effect. So if you look at our effect size here for the Etta squared, you can see that we have a large effect. Now, I think, and I'm not sure who agrees with me on this, but I still think I think the omega squared effect size is more appropriate for an ANOVA. So I'm going to illustrate that for you, and I think it's got a lot of symbols in it. So let me get ready and go back over to the Blackboard. All right, so guys, the omega squared which is a Greek letter, we might just call it W squared. And the way this is calculated is we take the sum of squares for the between term minus the degrees of freedom for the between times the mean square for the within divided by the sum of squares total plus the mean square for within. Now guys, I never remember that. I can't remember it. I always have to look it up and write it down. So guys, write this down somewhere, and you know, where you can access it when you need it. Guys, the square root of the W squared is actually our effect size. And the benchmarks for this tend to go from 0.01 to 0.06. Alright, the benchmarks tend to go 0.01, 0.06, and 0.14. Again, you're always going to have three numbers on your effect sizes: small, moderate, and large. All right. So, gang, let's go back over to R, and let's make this calculation. Now, what I would like to have, I'd like to have my my Anova output right in front of me, so I don't have to scroll up and down. So, guys, the first thing we have is the sum of squares for between, and then I have minus, and I have my degrees of freedom for between times the mean square for the within term. Now I want all that divided by the sum of squares total. Now guys, sum of squares total, R doesn't give you the total line, but you can just see that we need to add those two numbers, 20.13 and 23.60, so that's going to what, be 43.63. And we have the mean square for the within term, which is 1.967. Now, this gives us our omega squared, so our effect size would be the square root of that. Okay, which is 0.60. So guys, based on our benchmarks, this is a significant effect size for the difference in quiz scores across sleep pattern. Now, I put all this emphasis on on effect size. Here's the rest of the story. Typically, at least in my opinion, effect sizes for the overall Anova aren't that interesting, because in the Anova, what we ultimately want to do is we want to look at the effect sizes, or at least the statistically significant difference across the pairs. Once we find an Anova that's statistically significant, As I'm thinking about something, there's a package. Well, okay, let me just go and complete a sentence. Typically, the effect sizes for the overall ANOVA aren't that interesting. What we'd like to be able to do is we'd like to be able to calculate the effect sizes for the individual pairs. So between 4 hours, 6 hours, and 4 hours, 8 hours, and so on and so forth. Now, there is a command, and so I'm struggling because I didn't write this down. It's Okay, gang, let's see if we can, let me get back over. All right, so to calculate effect sizes for pairs, we're going to use what's called the MES command in R. And the MES commands requires you to put in 6 things. The mean for group 1, the mean for group 2, the standard deviation for group 1, the standard deviation for group 2, the sample size for group 1, and the sample size for group 2. So it's really easy to remember what goes in there. But so let's go back and just take a look at the differences. Now, to keep from scrolling up and down and stuff, what I'm going to do, I want this information right in front of me. So I want quiz sleep mean, and I want to apply quiz sleep standard deviation. And our sample sizes are 5 here, but let's say that we have a more elaborate data set, a larger data set. What you can do here is you can do length. Length gives you the sample size in each one. Now, so what I'm going to run here, let's just do first of all, as an illustration, let's compare 4 hours to 8 hours. And this is where the statistically significant difference occurred, okay? So I would run MES, and the mean of the first group, I'm going to do 8 first and 4 second. So 5, 2.2. My standard deviation was 1.58 and 1.30. And we had 5 in both. Okay, I was afraid that was going to happen. Darn it, darn it, darn it. Okay, I think I know what it is. Guys, we need to install a package for this, and I'm pretty sure that we have to install what's called calculate.es. Okay, let's try library. Well, guys, I'm going to have to get back with you on this one. Huh, I don't know. Well, I'll tell you what. I'll just show you what I would do when this happens. I would go to Google and I would Google it, and I would do MES for R. And I'm getting all sorts of goofy stuff. Well, we've done all this stuff. Got them crashing and burning here. Effect size are, let's go across groups. Don't want that. Okay, it's measured. Let's try this. Well, guys, I don't know. I'm going to have to get back with you on that one. The MES, I've used the MES command before, so I don't know what's going on. So let's get out of this. But I will not leave you hanging on this. I'll actually figure it out and put up a short video on it. It's embedded in some package. Obviously, it's not the one that I thought. But anyway, I'll figure that out. Now, one more thing I want to talk to you about. What happens when things go wrong? For example, what if we don't have normality? Guys, if it were me, I wouldn't do any transformations. I would run the Anova and report that we didn't have normality. I'd report the results of the Shapiro test, and I would report it, but I'd also dive into the literature somewhere, and there's plenty of information out there that says the results aren't off, that the results are fairly robust when normality is violated. What happens when we violate the homogeneity of variance assumption? Well, what I would do here, if I were doing that, I would run a different type of test. And guys, there's something called a one-way test, which we put in our quantitative variable tilde across sleep. And what this will do, it'll give us a standard one-way Anova with different degrees of freedom. And I have to confess I don't know right offhand how those are calculated. But you'll see that it doesn't assume equal variances. So there's been some correction in the calculation of the p-value to not assume that there are equal variances. Notice in this case, if we don't have equal variances, then we don't have a statistically significant result. But in this case, we could assume equal variances. But I'm just again, what would have happened if we had, I always tell students, what happens if you go out and you've written this big grant, $1-2 million, whatever it may be, and you go out and you collect your data, and you start checking your assumptions, and they're not satisfied. Do you just send the money back and wait? No, you don't. You make adjustments. And this is what you would do if you were running a straightforward Anova and the equal variance assumption wasn't satisfied. All right, gang. As you'll see in the write-up, I actually got this to work earlier. So I actually calculated the effect sizes for the differences. So again, I'm going to have to work on that. I don't know why it didn't work in the illustration here, but I will figure it out and I'll get back to you. So guys, how I would write this up, I have it written up right here. I should have had it open. Okay, so if I was going to write this up, I would say that there was a significant effect of sleep level on quiz score, and I would report the F, obvious reasons, or an F statistic, and always in parentheses will be at degrees of freedom, and F has 2 degrees of freedom. Our F statistic was 5.12, and remember that our statistical significance was only at the 0.05 level and not the 0.01 level. What you do here is you report the level, the smallest level at which your test was statistically significant. The next thing I did, I had to go into symbol to make this W happen. So if you go up here and go into insert and come down to symbol, go to your symbol browser and you can find all your Greek letters. Okay? So I said, despite a large effect, Bonferroni post-hoc test revealed non-significant differences between 4 and 6 hours sleep and 6 and 8 hours sleep. And I said a statistically significant difference was revealed between 4 and 8. Guys, these p-values that I'm reporting right here came from the Bonferroni T-Test, or the Bonferroni paired T-Test. These D's that I report right here were the effect sizes for the individual T-Test. And that's where it came from, the MES. And again, guys, I got this to work earlier. And again, I don't know why it didn't work now, but I will figure that out. So, guys, that's all I got. This was a pretty thorough illustration of how to conduct an Anova. So have a good one.